Morning, welcome to our next last lecture. I'd like to start out by giving you a sense of what we're doing for the rest of the semester. It's pretty brief, 2 more lectures, so hang on for a second. I'm looking forward to this. What I want to do with you is go back through the curriculum, not all of it, but the main points that I have up on the screen, review some of the basic ideas that we went over, and then extend them a little bit. In some courses, I've had the opportunity to do this, a quick review going back through the curriculum, and there's been a lot of benefits. So without much ado, we're going to get started. That is a pretty complete list of what we're going to do for the rest of the semester. I believe we're going to be able to touch on all of those 7 topics. If we fall short, obviously I'll let you know on lecture number 2. All right, so the first topic was chapter 2. In chapter 2 it was fluid statics, so fluids at rest. And the extension that we're going to do could be called action at a distance. So let's just start by reminding you a couple things. We took a look at enclosed fluids, and hang on for a second. Looks like I got a little bit of glare there. I hope that is better. So in chapter 2, we did fluid statics, fluids at rest, and we were able to get pressures at any point in the fluid. One particular application we took a look at was U-tubes, and we got the idea that because of a basic pressure relationship, the pressure at any depth would be the same. So, really quickly, you ought to be able to pause the video and say, okay, I'm going to figure out the pressures at those different dots, and give you a second to do that. I mean, obviously, over here at this top dot, the pressure would be the same as that pressure right there. So those would both be 10. As we go deeper in the fluid, the pressure becomes greater, and our basic relationship, hopefully you have that, but if not, I would encourage you to write it down as you're getting ready for test 3. The increase in pressure as we go deeper into the fluid is given by delta P is equal to rho GH. Okay, that is all old news. But what we're adding to it is just the slight additional idea. What if we had an enclosed fluid like this, and at this point, we added an additional 5 units of pressure. We had something that pushed there. Well, how would the numbers change? How would the numbers end up changing? Well, hopefully your intuition's good, but let's just go through it really quickly. First of all, this pressure that's added, maybe something's pushing right there, it is creating a compression, okay? It is creating a compression there like that. And that compression is going to travel through the fluid at what speed? Well, at the speed of sound in a fluid. And for purposes of a lot of devices that use applied pressure to a fluid, that's virtually instantaneous. So this compression is going to travel and spread through the fluid and make it over here almost instantaneously, as long as this enclosure is not huge. Okay, the next thing is Pascal's principle, which basically says that the increase in pressure in a closed fluid travels undiminished to all points in that fluid. Okay, so that increase in pressure of 5 right at that point is going to take this pressure and make it equal to 15. Okay, it's going to take this pressure and make it equal to 25. It's going to take this pressure over here and make it into 30, etc. So you're going to have an increase if we were in units of 5 psi, of 5 psi all throughout the fluid at every single point. So first of all, kind of an interesting idea. Second of all, how do you actually apply that? Well, there are 2 main ideas. First of all is the idea of action at a distance. So what if this is you and you want to lift this red object over here, and it's a distance away from you, and for some reason you don't want to be over here? Well, what you could do is you could run some tubing and enclose some fluid going all the way to that tubing. And what you could do is you could push down over here on a piston, and that's going to increase the pressure in this fluid right over here. Well, what does What do our principles of fluids actually say? Well, first of all, that increased pressure is going to travel all the way over here. It's going to travel really, really quickly, almost instantaneously. And secondly, most importantly, it's going to travel undiminished. That's the key word. So if you exert 10 psi over here on this piston, that 10 psi is going to travel over here to this piston, and it's going to be actual, that pressure then is going to raise this object over there. So action at a distance, there are all sorts of hydraulic systems. Hydraulics is a word for basically enclosed fluids, where we actually run tubing and we create a force somewhere else by using a force at a distant point. So that's interesting. You know, we can take some tubing, just some cheap tubing like this, enclose some fluid in there, and we can take a force here and have it be applied over here like this. And this tubing could be 10 miles long, and it's going to take the force at one point and bring it to another point. Okay. What's more important as far as applications is the idea of mechanical advantage. So just a quick review of that. Mechanical advantage is a really important idea. So just a quick reminder on mechanical advantage that hopefully you've seen in your dynamics and physics classes. If we want to lift something like 200 pounds, well, that's tough for us. We can do it. We are, as human beings, we're good at exerting small forces for a continual period of time. We're not great at exerting huge forces. So 200 pounds would be something tough to do all day long. Obviously, we're going to use a ramp or something like that to make it easier. And you guys have done your ramp forces. If you think about it, if you take this block and put it on the ramp, the force down the ramp is given by the weight times the sine of the angle. And so I get 100 pounds there. So if this were on the ramp, I would only need to push with 100 pounds to get up the ramp. And that's a lot better than 200 pounds. We could even go with a smaller angle and make this force even smaller. Okay, you might want to write this down. Basically, the idea of mechanical advantage is it's going to be the force that it would take to do a job without the machine to the force with the machine. So the mechanical advantage of some sort of simple machine, be it a ramp, a screw, a pulley, etc. So in this case, just taking a look at how the numbers work, if I wanted to lift this without a machine, it would take 200 pounds of force. And so this numerator right over here would be 200. Instead, if I decide to employ the machine, it's only going to be 100 pounds of force. So we're going to say the mechanical advantage of this wedge right here, this ramp, is 2. Now, as you get into more complicated machines, it's pretty easy to think, wait a minute, is there some sort of violation going on? You know, it seems like we're getting something for nothing. But the answer is no, we're not. In this case, we only if we wanted to lift this, say, a height of 4 feet, we'd only need to go up 4 feet like this. Whereas if we use the ramp, we have to push it further. So with simple machines, we're using less force over a longer distance. And as humans, that really works out to be a good trade-off for us, because once again, we are good at exerting small forces continuously. If we want to do things by human power, we can get a lot of great things done by using simple machines. And of course, that's employed a lot of times even if we use motors or things like that. Right, a simple example that is actually not uncommon out there at all. There are hydraulic jacks that essentially have an arrangement like this, where there's an enclosed fluid, and each of these circles essentially represents pistons. I maybe should have given a little bit of a depth to that piston. And what you could do is you could push here, and then the pressure would go through and create a similar create a push over here like this. Or conversely, you could push at the small piston. And think about it for a second. If you were trying to multiply your force, would you want to push at the 6-inch piston or at the 3-foot diameter piston? And if you think about it, what you want to do is you want to push here, and let's see how the numbers work. So let's say over here you have some sort of large object that you want to lift. It's at a distance, but what's more importantly, you want to do it without a lot of force. You want to multiply your force. So let's say over here, you end up exerting 50 pounds of force. Okay, so you got this 6-inch diameter disc, and you push down with 50 pounds of force. So that's 50 pounds. Okay, what's the force over here going to be? Well, Pascal's principle is the idea that you create a pressure here, and that increase in pressure travels undiminished. Every single point in that fluid's pressure increases by the same amounts here, including, most crucially, this point over here. So what we should do is we should do a quick calculation and get what P1 is, and I'm going to do that myself. So not great pressure. I got that the increase in pressure at this point 1 over here like this is about 1.77 psi, being a little bit higher. In any case, what's going on with that then? Well, that increase travels throughout the entire fluid almost instantaneously. And over at this point, there's going to be the increase as well. So we can say, look at P2, there's that same increase of plus 1.768 psi. And that's going to allow us to figure out what the force that is created by this fluid at this point right there on that disk. And that is just a rearranging pressure is equal to force times area. And once you go ahead and pause the video and make sure you got that number right, if you got it right, then work out the mechanical advantage. All right, so it worked out pretty well. There's my math. I didn't do the units, but you guys ought to be able to follow it at this point. This is pounds per inch squared. So I should do my area of that second disc in inches squared. And when you crank through it, I get 1,800 pounds. So it's worth pausing to appreciate that. You push over here with 50 pounds of force, which a human's totally capable of doing, and you end up lifting an 1,800. You could lift an 1,800 pound object over there like that. So a huge mechanical advantage. The mechanical advantage is essentially the force the job would take without, or divided by the force that it's going to take with our machine. So we're going to lift an 1,800 pound object, and we're only going to exert a 50 pound force. And I believe if you crank through that ratio, you're going to get 36. So you're going to get 36. Is there any magic to it? Well, basically, if you think about and go through the geometry of it, you're going to have to push a longer distance here than the distance you push over there. So on an energy front, energy in is going to be equal to energy out, but we sacrifice working over a greater distance for exerting less force. And of course, this is the type of setup that's a lot of times in auto shops where you have a hydraulic jack that over here you could actually have a car and you could exert a small force over here to raise something out. Just raise something up. Okay, quick review of chapter 3. So chapter 3, probably one of the main things that was emphasized was the Bernoulli equation. So just a quick reminder on that. That was a case where we had a fluid and it moved from a point 1 to a point 2. And the Bernoulli equation is one form of the Bernoulli equation is written down there. And a great way to think about it is that this combination here, the pressure, something to do with the speed, and something to do with the elevation, is essentially giving us the mechanical energy of the fluid. And so this equation is saying that basically the mechanical energy of the fluid at the end of our process is equal to that at the beginning of our process. Okay, is that always true? No way. I mean, we spent a lot of time in chapter 8 looking at the fact that fluids lose energy in pipes because of viscosity, because of frictional effects. But in many cases, it's not unreasonable to say the fluid is incompressible, that it follows streamlines, that viscous effects are negligible, etc. And we can use this idea. And the application that we're going to look at as we review chapter 3 is how do we measure fluid speed? So let me get a drawing up there to give you a sense of how we could measure fluid speed using this Bernoulli relationship if we assumed it could be applied. So what I want you to do is imagine a fluid going really fast like this, okay? And I'm going to call that point 1. Okay, and then we're going to imagine that in the fluid stream, we put a small pressure probe right there, and that will be point 2. Okay, and we're going to imagine that this fluid over here, this line over here goes past it, this line over here goes past it, etc. But what about this line right here? Okay, well, it's going to slam into it, and the velocity speed is going to become pressure. So what we're going to have actually, if we take a look at this equation, if we have no changes in elevation, and just to rewrite that equation, well, why don't you go ahead and pause really quickly and see if you can get that written down correctly and think about how we're going to use it to get fluid speed. All right, so hopefully you wrote that equation in blue. So basically our final point is right at the tip of this pressure probe, and our beginning point is out here where this pressure device hasn't affected flow at all. And for this flow that goes from here to here, we could imagine it along a streamline, and we could say that the pressure that we get at point 2 is equal to the pressure we have at 1 plus 1/2 rho v squared. This fluid here would have both static pressure, P1, and it would have dynamic pressure. There's no change in elevation. So if we could measure this pressure here and measure this pressure here, if we had numbers for this, like this was 40 and this was 30, obviously, if we knew the density of our fluid, we could use that equation to solve for speed. And that has been like a fundamental issue as you go through the history of fluids. How are we going to use this basic relationship, which seems to be true and is often true, to get fluid speed? And there's some clever devices that do that. Let's take a look at the pedostatic tube. So there are all sorts of clever devices that involve using some really simple tubing like this and arranging it so that a portion of the tubing is exposed to the airstream twice. So I got this portion right here that would be exposed this way. And then the other portion is arranged in essence so that it is actually facing the flow there like that. And then some sort of fluid is put in that tube. Usually it has some sort of tinting in it so you really clearly see it. Okay, well, I'm going to call this point 1 and this point 2. And just imagine this tubing is small compared to this fluid stream going along. By the way, this fluid stream doesn't need to be air. It could be any sort of fluid stream. And what I want you to do is pause the video and think about how's the pressure at 1 and 2 going to compare? All right, so one way of thinking about it is to take a look at just this streamline right here. It's coming along, it's passing right over the top of this opening, and it's going straight into that opening right there like that. Okay, you probably got it. It might also be worth writing the Bernoulli equation for that streamline. No z terms, because there's no change in elevation, okay, from this point here to this point here like that. Okay, well, taking a look at how that equation is going to simplify, what were using terminology from earlier in the semester, this fluid stream right here is going to stagnate right there like that. Boom, it's going to hit and be stopped. So the pressure here is not, at point 2, is not going to have that speed term. So we can actually just erase that term right there. And there's going to be our Bernoulli equation for this relationship here. I'll move that P2 over so it's a little bit simpler. Okay, secondly, what's actually going on with pressure? Okay, well, at this point here, press on this, maybe if this is air right here above some sort of fluid, the pressure of this air is just static pressure or sideways pressure. Maybe it's 14.7 psi. But over here, we have that speed pressure converted to pressure. And so over here, we're going to have a greater pressure. And what you would observe then is, because there's greater pressure here than here, is this tube, this portion of the fluid would move down, and that portion of the fluid would move up, okay? And so there is a pardon my arm, there's a classic drawing showing what's going on. So what we're gonna actually do, and what you'll actually do in, say, ME128 in lab, is you're gonna use this distance here to get fluid speed, okay? Because we know, basically, that the pressure at this line right here is constant. The pressure right here and the pressure right there is constant, okay? And so we can go up here like this, and we could call this pressure right here P1. P1 is going to be less than P2, or in other words, another way we could write the equation is P1 plus this height right here, rho GH, is going to be equal to P2. So there's a bunch of different ways you could express that, but you could say P2 is bigger than P1 by this distance rho GH. Okay, and being careful, what is this rho? Is it the density of this fluid out here, or the density of the fluid in the manometer? It's the density of the fluid in the manometer. So maybe we should call this F for fluid and M for manometer. Okay, sorry about that writing a little bit small. Okay, what I'd like you to do is see if you can do the algebra and solve for the speed. All right, so taking a look at the reasoning, I took this formula here and I solved for P2 minus P1. The difference in the pressures is that 1/2 rho v squared term. In addition, I could take this a second equation and solve it for P2 minus P1. And the difference in pressure is essentially how much of a swing we get in this manometer measured in terms of pressure, rho mgh. So obviously, just taking a look at the algebra, these two terms need to be the same. And there is probably like the most important equation you could write down out of this. Caution. There are so many different types of scenarios that you might see out in industry. And the principle more that leads to this equation is what's important. I'm going to give you 3 or 4 homework problems that are not going to be long, but require you to think a little bit to come up to the answer. So I would refer back to this and see if you can use this sort of thinking. In this particular case, though, if I solve for v squared, then I get 2 rho mgh divided by the rho of the fluid in the manometer. And let's just see how that turns out. Okay, so let's imagine that we use a pitot tube with air. It's done all the times. Many small aircraft still have pitot tubes in them that are used to figure out airspeed. And basically, this would be our equation we would use. Let's say that there's water in the manometer, okay, H2 in the manometer, and that difference in height ends up being 6 inches. Well, how fast is the plane going? Okay, remember we could think of the plane as being stationary and the air moving past it. So let's go ahead and solve for that v and see how it turns out. By the way, I should have said in this case, what we're going to do is we're just going to use standard values for densities from those tables that we've always been using. If we had different temperatures, different pressures, like elevations, etc., we'd have to be more precise. All right, so putting in the numbers, in the numerator here, we've got the density of the fluid in the manometer, so that's water, so that's 1.94. We've got G, which could be 32.2, and the height, we want to be consistent, is in feet, so that's 0.5 feet. The denominator is the density of our fluid that is actually moving, that we're taking the speed of, and that's air, so that's the standard value is 2.38 times 10 to the negative third. Obviously, you could find other densities by using the ideal gas law or tables in the book. Okay, and when I crank through that, for v squared, I get a very large number. The units work out nicely. The slugs go away. The slug per foot cube goes away. And I'm left with feet squared per second squared. So then I just need to do the square root on my calculator. Hopefully, I wish I was in class so I could get a check for you guys. But I got 162 feet per second. Okay. And if you remember, I mean, that rough calculation, 88 feet per second is 60 miles per hour. So just doing that quick conversion, I get this plane would be going about 110 miles per hour. So if you have a water manometer, it doesn't need to be very tall to get the type of speeds that a small aircraft would end up doing. And those are a big part of small manometers, pardon me, of small aircraft operating a static pitot tube. All right, so chapter 3 takes the approach where we follow a fluid from one point to another point and try to write an equation saying that the energy the fluid has here and here is the same, it just might have changed form, and that is the Bernoulli equation. Chapter 5 is what's called the control volume approach, where we see some sort of device operating. It doesn't necessarily need to be a device, but often it is, like this fan, and we try to analyze in and out and try to write equations that allow us to solve for whatever it is that we want to solve for. So if this fan were operating, it's kind of hard to see, but that blade spinning right there. We're going to get some sort of airflow in over here. We get low pressure over here, and so the air gets essentially sucked in, we say. But strictly speaking, there's not a force of suction. There's just low pressure that causes it to go in. And over here, we have the fluid coming out at higher pressure. Well, how do we go about analyzing that? So to remind you on chapter 5, what we did was we took our whatever device we were looking at and we imagined a dotted line around it to form what's called a control volume. So for a fan, the control volume might look like this, where I have this dashed line representing the fan boundary, and I have fluid flowing in at these surfaces here and fluid flowing out these surfaces there. Sometimes there's nothing going on those surfaces. And we got through 3 types of equations so far in chapter 5, and we're going to do one more. So the first one was, what if we tried to write an m dot equation, a flow equation for mass flow? Well, that worked out pretty well because we in ME120 just focused on steady state, and so we could say that m dot 1 is equal to has to be equal to m dot 2. And there were lots of permutations of that equation. It turns out it can be very useful. Sometimes it's called the continuity equation. Okay, after that, we went over momentum, linear momentum, and we compared linear momentum flow in and linear momentum flow out. They were not necessarily equal. And so basically one idea we had is the net force on the fluid as it goes through whatever device we have is equal to the change in the linear momentum flow. So this would be linear momentum flow out minus linear momentum flow in. That was the second analysis we did. The third analysis we did was angular momentum flow, and that worked for things like sprinkler heads, which are spinning. We could compare the angular momentum flow in, angular momentum flow out, and instead of getting us net force, they got us net torque. Okay, and then if you look through chapter 5 or just think about it, hey, one main quantity that we think about in engineering and in physics, et cetera, that we haven't done is what about energy? Does energy out have to be equal to energy in? Well, in this case, one of the two is going to be bigger. For this fan, one of the two is going to be bigger. And it should make sense to you that the fluid, the air energy going out is going to be bigger than the air energy going in because the fan is actually pushing on that air. So the energy equation is going to be a little bit more complicated than out versus in, but we can fix it up very, very simply. So we'll get started on that in just a second. So what we're going to do is to derive or make sense of a mechanical energy equation for steady state control volumes. All right, so this represents some sort of arbitrary control volume and a fluid's going in there, and there's 2 and there's 1. Does energy at 2 equal energy at 1? Well, if we're back in chapter 3, that was the assumption we made. We assumed that there were no frictional effects, there was nothing that added or removed energy, etc. So we could write that equation. Okay, and we can express the energy in a variety of forms. That's one of the primary ways we did that. Okay, another way we can do it is, and I won't write this down, but just a reminder, many times the form of the energy equation is written by dividing everything by density, and we can do that if we assume that the density change is insignificant. Let's just look at one of those terms. No need to write this down, but let's just see if we get units. What are the units for P over rho going to be if we're in SI? And I would encourage you to pause the video and see if you can remind it. If we're in SI, what are the units for P over rho going to be? Okay, as usual, the more you do yourself, the better you get at this you get. So if you weren't sure what to do, there's your starting point, but we want to simplify it. And to give you a hint, we want to leave the newtons in there. See if you can finish it off. All right, so A minus, if you got this far, Newton meter per kilogram, and that's just simplifying this expression right here. But important reminder, what are we doing all over here? We're trying to work on energy, and do you see any energy units in there? Absolutely. A Newton meter is a joule, so this is a joule per kilogram. Okay, what's the point of all that? The point is that if we write our Bernoulli expression in terms of units of pressure divided by density and the corresponding term for these other ones, every single term gives us, for our fluid, a measure of energy per unit mass. Let me write that down really quickly. Okay, so this term gives us the pressure energy in joules per kilogram. This gives us the speed energy in joules per kilogram, and this gives us the elevation energy in joules per kilogram. And in chapter 5, this is the form of the Bernoulli, of the fluid mechanical energy expression that the book really likes to use. So we're going to go with that as we go through this derivation. Okay, so for our control volume devices that we're doing in chapter 5 is E2 going to be equal to E1, where E could be thought of as specific mechanical energy, and that's the combination of the pressure energy, the speed energy, and the elevation energy. Well, taking a look at this case like this, would E2 be equal to E1? All right, well, hopefully you're going to say no. In addition, you might say, hey, if you got a fan like this, you would call up the manufacturer and say, hey, you got anything better? Because you would like a fan without a lot of frictional or rubbing effects for your air. And as the air has to make this turn here like that, man, that's a pretty abrupt, quick change. And there's probably going to be some energy loss. All right, so there's two things going on, reasons why E1 wouldn't be equal to E2. First of all, the fan's going to add energy. Secondly, there are going to be frictional losses. So a better way to write our equation would be that the energy coming out of our control volume is equal to the energy the fluid has coming in, okay, plus any energy added by work. Okay, and so the book uses a lowercase work, W, where that's joules of work per kilogram. They call it shaft work. And of course, most devices that are in a control volume that spin and add energy are going to have a shaft. And then there's going to be losses as well. And they use the lowercase l for the losses. And that basically is roughly the form of the energy equation that we're going to end up using in chapter 5. What we're going to do, to be more precise, is we're going to replace it with all this here. And let me pause and get that equation up there for you. Okay, so what we're going to ask you to do for test 3 is take a look at control volumes and do mechanical energy. So this is equation 5.82, and you could write it down like that. Personally, I like to add some parentheses in there. It helps me think about what's going on, so I'm going to put some parentheses there. And in short, then we could describe this saying, look, the energy the fluid has coming out is equal to the mechanical energy the fluid has in, plus any energy added by, say, a pump blades or a fan blades, etc., minus any sort of loss. Okay, and that is a very powerful equation. We'll ask you to do some practice with that and understand what's going on as far as energy. All right, let's work an example to feel how this is going out. So we'll do a fan, okay, and we're asked to use energy essentially to figure out, hey, how much work is the fan doing on the air in joules per kilogram? And then I'm going to ask you, if you get that answer, to think a little bit and say, hey, at what rate is energy being given to the air in watts then as it moves through? Okay, so some data. Let's say that we know that the mass flow rate we want this fan to produce, 2 kilograms of air per second. And we've got the air density as 1.25 kilograms per meter cubed. This second one might come from the ideal gas law. Okay, we're going to assume that the fan is kind of like this fan over here like this, where it actually pulls still air to the inlet of it. So V1, actually, this air over here is basically going to be virtually zero speed. And that's a common assumption. It's going to come out pretty fast, 10 meters per second, so that's about 20 miles per hour, okay? And some other data, it's going to come out with a little bit of pressure relative to standard pressure, 100 kPa gauge pressure. There's going to be some loss as the air goes through there because it's a poorly constructed fan and there's friction of 2 joules of energy loss for every kilogram that goes through there. Okay, that is enough. Why don't we go ahead and pause and see if you can set up the energy equation, the mechanical energy equation, and go through and solve for the work of the shaft. Okay, per usual, what we would like it to do is take our equation, and if there's any terms that we can eliminate, simplify. So hopefully you notice that we can think of this flow as basically being constant elevation. So the elevation terms go away. All right, taking a look at the inlet. Here's the inlet energy. All right, so we said basically the fan pulls air with zero speed, okay? And that goes. So this inlet stuff's looking pretty easy. How about P1? Well, P2 was given as gauge pressure, pressure above atmospheric pressure. And at this fan inlet, it's pretty reasonable to assume that the air that's pulled in is at atmospheric pressure. So in this case, we're going to make that assumption. We'll give you more practice on homework on making that assumption. So all these terms end up going away. So if we take a look at the result, then basically what we want to do is fill in this equation right here and go term by term. And I'd like you to get some numbers, and I'll get the numbers up there and see how that turns out. So finishing it off, for P2 over rho, I got 80, okay? For V2 squared over 2, I got 50. So we have a total energy coming out of this fan of 130 joules per kilogram. And so you might think, oh, that must be what the shaft must do. It must provide 130 joules to, or the fan must do, it must provide 130 joules for every kilogram of air going through there. But if it comes out of 130 and there's a loss of 2, it's got to make up for that loss. So the answer for the work of the shaft, you can do it algebraically or just thinking about it, is that the fan has to provide 130 joules of mechanical energy for every kilogram of air that goes through there. Pardon me, 132. And there's our answer. Okay, how about the additional question to think about? How about the rate at which energy goes? Well, if you think about, we didn't use this number here. There's 2 kilograms per second of air going through that fan. And you can reason it out then. 132 joules need to be added each kilogram, and there's 2 kilograms per second going through there. Well, if you just reason it out or even do the multiplication, you can just multiply those together and get the power that's going to the air, which would be 2 times 132, 264. And if you look in a book like that, it's not going to write it as joules per second. It's going to write it as watts. Okay, and that would be the power that goes to the air. Then you might be able to figure out the power of the motor or whatever else that runs the fan. And this is not going to be a 100% efficient system, so we're going to have to provide more power to the motor that drives this shaft, and it might be in the order of 500 watts. That last thing, I didn't give you enough information to work out, but for problems on homework number 10, you will get that and be able to come up to that conclusion. So last topic for today, we want to come out of this course knowing how to say size pumps and fans. And so for starters, you actually know how to size a pump that would need to get a fluid, say from here over to here like this, okay? The idea would be is that as the fluid goes along, it is losing energy due to friction. And as it goes along here, it's losing energy due to friction. Well, if you want the fluid then to move from here to here, you've got to provide enough energy to overcome that loss. And that's how you size the pump in part, is to figure out, okay, how much loss there is, we're going to overcome it. Okay, what that ignores, though, is the fact that in a lot of our piping system, we have more than pipe. So to take a very crude drawing of, say, like a cooling system in your car, we got some sort of coolant, and it circulates through your engine and picks up heat there, and then it goes over here to the radiator and dumps its heat and comes back here like this. And there's a lot more than pipe. So it's going to take a little bit more work. But before we get started on that, let's just remind ourselves about, hey, what are some different forms we could write the mechanical energy equation in? If we were doing this and we wanted to get down to basics, we would think about the energy the fluid has when it comes out of the pump, mechanical energy, versus the energy it has after it completes that circulation and comes back. So just think about it for a second. I mean, is E2 going to be equal to E1? Is the energy that it has when it gets over here going to be the same as the energy it has over there? And no way. Chapter 3, the Bernoulli equation, we assumed that was true, but we were assumed that there were no frictional losses. Man, if you have engine oil or something like that that has high viscosity and it makes a round here like this, or some sort of coolant like a glycol type coolant, there's going to be losses. So our equation would be E2 is equal to E1 minus the losses that occur along the way. All right, so that is very similar to what we just did a few minutes ago from chapter 6. As we go from 1 to 2, there is no pump along the way or no shaft along the way, so that works of shaft term would go away. All right, how are we going to express the energy terms? All right, well, we have 3 main options, maybe more. We can express the energy in terms of pressure. That's really, really common. The next thing to do is we can divide everything by rho and get an equivalent term for the energy. And I'd like you to try to do that yourself and write that down. Divide each one of those terms by rho. Okay, so there's a second alternative for the mechanical energy of a fluid. And we could take a look at this term here in thinking about units and say, oh, if we were in English units, that would be foot per second squared, and that's foot. So this term right here would be foot per second squared. And that's a valid expression of it. But if you go through it, every one of these terms is equivalent to energy per unit mass. So in SI units, it would be joules per kilogram. And that's what we did just a few minutes ago. Okay, the third way the mechanical energy term for a fluid is expressed is going one step further and dividing each of these terms by G. And so why don't you go do that and think about what each term's units are going to be. Okay, so here's the third option, is that we can express these three terms as shown right here. Okay, what are their units going to be? It's going to be easiest to take a look at that term right there. What are units for H? H is like a height, okay? I could have used Z, by the way. And so our units, if we were in English units, would be feet, equivalent feet of water. So we can think about the energy of a fluid in terms of its pressure. We can think about it in terms of its joules per kilogram, or we can think that that energy the fluid has is equivalent to a certain number of feet of water. So what we just did has to do with the way we think about losses in fluid systems. There's two most common ways we do it. So going back to what we did in chapter 8 earlier, we actually went over major losses, which are oftentimes termed pipe losses, and we got it in terms of pressure loss. So going back and reminding you really quickly, once again, what we can do is we can do this term 1/2 rho v squared. That's termed the dynamic pressure, and we can think about the loss as being related to how much energy the fluid has expressed as pressure. Okay, then we said, hey, for some sort of pipe, like the pipe going from here to here, that length right there, we could take the length and divide it by the diameter, okay? And that was our second term. Sorry if my board's a little out of place. Okay, and then in addition, there is a term for how much friction there is, and that came from the Moody chart. So that is our basic way of figuring out pipe loss that we're going to want you to be able to do once again on test 3. In addition, it's common to take this term right here and divide it by rho g, and let's get that other form up there. Divide that term on the right by rho g and see if it can remind you what that actually gives you. Okay, so this formula then is equivalent to this formula right here. We got the rho gone because we divided by rho, and then we introduced the G there. And this gives us the loss in a length of pipe in terms of units of, say, an SI, feet of H2O. And this is really common out there in industry. Both are valid. This is used a lot. And that's going to do the pipe. Okay. How about this right here, this elbow? This is pipe, but the dynamics are much different. Remember when we did this section right here, we thought about things like shear and velocity profiles and fully developed flow, and that allowed us to use this equation here like this. But as we go through this elbow, everything's different, okay? The fluid ends up taking a turn. There can be lots of banging against the walls that lead to friction, etc. So there's no way we can actually apply this formula. So that would be a huge challenge to go back to your basics on fluids and see like, okay, for an elbow or for a T or for some other thing that's part of a piping network, how are you going to get the losses? And what has come up is the idea of just doing testing, which for any type of elbow gives us a coefficient that we can use. So what I'd like you to do is pull out chapter 8, and we'll take a look at some of those coefficients and how they're used actually to get the pressure loss, or what's more commonly termed the head loss for fittings. So I'm looking at page 434, and I encourage you to go there yourself. But what they have is a typical fitting, which is a valve that's part of a system. And it's kind of interesting. They've done a nice job of taking a look at what the streamlines are looking for, like. And you might ask yourself, hey, is that going to be laminar flow or turbulent flow through there? And at any sort of significant Q, that's going to be turbulent flow. And trying to come up with some sort of theory that gets the loss, there's just no way. So what we do is we keep that V squared over 2G term. That V squared over 2G term is once again an energy term. It gives us the energy of the water going through, or the fluid, I'm sorry, I should say going through in terms of feet. And then it's the responsibility of a manufacturer to provide a K value. And you can find those all over the internet or from various suppliers. All right, so let's go ahead and take a look at some particular K values, and we'll focus on a main chart for now. Okay, so on page 440 is a table for typical pipe fittings. And I'm just going to start by having you guys look at the table there for the 90-degree elbows. Okay. So basically the idea is you have some sort of fluid approaching an elbow with a speed V, and you want to figure out, hey, what's the loss there in that elbow? Well, you're going to do V squared over 2G, and then you're going to pick the appropriate K value. So taking a look at that, you can see there are various K values. I'd like you to look at the threaded one. That K value is large, which means that the loss is going to be large. But if you think about a threaded elbow, when you put a threading in it, when you have threads, there's a lot of changes in diameter associated with the threaded connection, and that's going to lead to turbulence and associated losses. On the other end of the spectrum, for the 90-degree elbow is the long radius elbow flanged, long radius elbow flanged, and that loss is much, much lower. Long radius means, of course, that the radius would not be some sort of very short quick turn, but a very gradual turn. And so then you get lower losses and you get much more efficient system. So finishing things off, a little bit of practice. So let's imagine that we're building a piping system and we've got 112.2 GPMs of H2O, and we choose a threaded elbow. Why would you choose threaded? Well, piping can come with threads on it, and then we can just rotate the elbow on there, save ourselves a lot of time. We don't need to sweat it on with like with copper piping. We can get out of there faster. But we should do a check. What's the loss going to be like? I want you to start with the regular equation and see if you can work towards getting PSI. Again, the more you can do yourself, the better. I encourage you to pause and start making progress. So breaking it down a bit, we want to, I'm going to do it following the book's approach, which is to call this a minor loss. It's strange that it's called minor because a lot of times the component losses are much larger than the piping losses. There's our relationship. And so a lot of this looks pretty easy, but reminder, we got to get the speed from the data given. So we got to do Q over A to get the speed. And we also need to get the KL. So if you haven't done so already, keep going and figure out as much of that as you can on your own. All right, intermediate step, I got 0.25 cubic feet per second for the flow entering that opening right there like that. That may seem small, but remember, a cubic foot is a substantial amount. And if you counted a second, 1/1000 cubic feet went in there, wow, that would be really moving. That's a preliminary step, and then we're going to use that to get the speed, average speed of the water entering the fitting. All right, so I ended up getting that the speed is 5.1 feet per second. So that water's moving pretty good as it enters that elbow. The KL I got from one of those tables in chapter 8. We'll ask you guys to use a couple of those tables on test 3, and then let's put it all together. So the minor loss is going to be KL V squared over 2G. And then substituting into my minor head loss formula, HL minor, I did 1.5, the speed squared over 2 times 32.2, and that works out to 0.606 feet. And that's normally the way it's done in industry if you're getting the loss of some sort of component. But just to put a little bit of feel for it, how about if we asked you to get it in PSI, what would that be? Well, just a quick reminder on some terms, it may be helpful to use and think in terms of the Bernoulli relationship. The pressure term is equivalent to rho GH. We can divide both these terms by rho, and we get a energy density like joules per kilogram term, pressure over density, GH. And then if we divide both of those by G, then we get H term, and we get the pressure in terms of some sort of height of a fluid. So we can think about rearranging this and just, this is a quick reminder of something that we saw earlier in the semester, the pressure we can get by taking the H and multiply it by rho G. So this term right here, this 0.606 feet, is feet essentially of water. So to get to the pressure, I would actually take that 0.606 feet and multiply it by the density of water, which is 1.94, and multiply it by 32.2. And then I'd multiply by the 0.606 feet. So I'll try that really quickly on my calculator and see what I get. So my calculator gives me 37.86. Could that possibly be right? Well, think about carrying through the units, okay? This is slugs per cubic feet. This is feet per second squared, and this is feet. And if you try to get that pound in there and you're careful, you'll notice that this is for pounds per square foot. So that's the pressure per pounds per square foot. So we need to divide that by 144. And when I do that, I'm getting about 0.26. So that would be the answer to this example, 0.26 psi, which would mean actually that if you had a pressure gauge here and it say it read 14.26, here it would read 14. It would be a lower pressure, and that's just due to the frictional losses as it makes that turn. And that is not trivial. And so you'll see actually as you go through and make pumping systems that you've got to take into account elbows. They're not really minor. They're just called minor as opposed to distinguish them from piping. Hey, let's just finish it off by just a thought question. What if part B was, what if we went it with 1 inch diameter instead? 1 inch diameter. We want to save some money. If you go to Home Depot and start pricing these, man, 3-inch elbows are expensive. Let's go with 1 inch. Well, just thinking through it and conceptually, why is there loss as we go from here to here? And that's friction and rubbing and turbulence, et cetera. Well, if we try to fit this much water through a small area, the Reynolds number is going to be huge, and we're going to get a lot more friction. Okay, but we're not going to go to the Moody chart to do this because this is a fitting. So how are we going to do it? Once again, we're going to use this term, this expression right here, and let's go term by term and think about how those terms are going to change. G, that's not going to change. KL, it's not going to change, but V is going to change. It's going to be huge. The speed is going to be huge, and as a consequence, you're going to get a much bit larger pressure loss. All right, well, that is it for today. The next thing for you, after you've got these equations down and thought about it a little bit, is to get going on homework number 10. I don't have it posted yet. I'm working on that, and it will take you through examples related to these concepts. Next lecture, we'll continue to go through that list I had. And again, I'm hoping that what this will do for you is allow you to review stuff that you had earlier in the semester and hopefully gain some more confidence about those concepts and then making stuff all a little bit more applied. More coming. Have a good afternoon, you guys.